I can see the audience. Hello, everybody. Yay! Success. All right. How much time do I have? Am I limited on time or? So like what, till 1:15 or just give me a limit. Anyway, if anyone is interested, if you guys are on Slack, I have a channel on Slack right now where if you have any questions whatsoever, you can ask those questions during my presentation at the very end. I do really apologize. I couldn't make it to the conference. I was really hoping to. I've been in Kiev once in my life. It was an amazing experience. I was really looking forward for another a trip to your city. However, my wife made an unexpected surprise, and she gave birth to my daughter, and I was stuck really here, moving between hospital and my house constantly. Anyways, I do thank you guys for being here. I'll try to provide a session remotely best I can. Can you guys give me a thumbs up or a thumbs down if you can hear me correctly? Like, all right. So let me share my screen. This should be, I haven't been using Slack for a very long time. Share screen, sorry, not Slack, but Skype. You should probably see my screen right now. Hopefully, yeah, all right. And now I should be, God damn it, play. Yay, all right. Do you guys see it? Hopefully you guys see it. I actually can see you. This is awesome. All right, so we'll go to my talk, formal specifications applied with TLA+. Right, so we have hopefully around 40 minutes. Let's do this. And yeah, all right, well, come on. There we go. All right, so this is Mercedes E-Class. This picture is actually taken from advertisement. And you might be looking at the advertisement a little bit closely, and you will see that they're advertising that this car is running on 25 times more code than a Raptor fighter jet. And when I first saw it, I was like, huh, really? Because if you Because if you go to Wikipedia, you will learn that F222 Raptor runs on 1.5 almost 2 million lines of software. That would mean that the car runs on 100 lines of code. That's absurd. That can't be possible, right? Unfortunately, it is. A premier car right now contains approximately 100 million lines of code, and it's actually being executed between like 70 or 100 microprocessors, all networked together. So you can think of your car, the thing that you drive probably more than 150 kilometers per hour, just as a little bit bigger distributed system. And you're closed in it, and you're probably not really safe in it. But you might be thinking, that's fine, right? It's fine. Car industry, it's always been safe. It's always been fine. Unfortunately, it isn't. So this is Jeep Cherokee, and what happened was those two white hat hackers, they convinced a wired journalist to drive the car while they'll be doing some naughty things to it. Within a few minutes, they managed to hack into that machine. They were taking control over the whole car, really. They were able to modify the air conditioning, the windows, the acceleration. Eventually, they turned off the engine. Unfortunately, when they turned off the engine, that car was it had almost collision with a truck. And this is how this little experiment ended up in the last place. But then again, what important thing is that the Cherokee, it was Jeep Cherokee, but it could be really any car. Those white hackers, they chose their little experiment based on this paper that was written at the University of Washington, when the researchers showed that any current modern car, especially premier car, can pretty much be hacked remotely from anywhere, any place in the world. But you might be thinking, come on, I mean, those always like just research, is academia, right? It's not really anything that applies to modern life. Well, it does. And if you recall, Toyota had this little unintended acceleration incident, and it might be, we might laugh about it right now, but you have to remember that people actually died because of it. The National Highway Traffic Safety Administration asked NASA experts to review Toyota's code and actually find if there were some potential bugs in it that led to that acceleration. It took them 10 months to do the code review, and they said they couldn't really tell whether it was because of the acceleration was because of the error in the code or not. When there was things were taken to the trial, another team of software experts were taken, and they took over when NASA left off. And after 18 months, they said like they found spaghetti code in Toyota software, and pretty much they said like there were 10 million ways to potentially lead to that to unintended acceleration. As in one particular case, there was a potential flip of a single bit in the memory that could lead to that problem. Another fun example for me is the 911 call. The 911 call in the United States for I think around 2013 stopped working during the night. People couldn't really connect. People couldn't say that we are being robbed or mugged or fire is taking place in their house. The thing was, the 911 phone calls were at that time being run by the software, which was running in Colorado. That company that wrote the software for 911 calls, well, the engineers forgot the integers. You know, the integers in our computer systems, they actually are bounded. So they are not limitless, right? But they had this little counter, which was an integer, and they were incrementing this counter every time somebody made a call. Unfortunately, that counter was also being used to create unique identifiers for events. When the counter became a negative number, all things went hell, and people couldn't use the system for a few freaking hours. Even though the company was putting some safety features into the software, they were only gathering the features that they knew about. There were this many features that they didn't take account of, and all hell broke loose. Interestingly enough, for the examples, is July 8th of 2015. So if you look at the morning of July 8th of 2015, few things would happen, really. So first of all, the New York Stock Exchange stopped working in the morning. The whole software broke, and there was no stock exchange happening whatsoever. Seattle's 911 system went down again, and at the same time, United Airlines were completely grounded because of the software failure. So at that time, early in the morning in the United States, everybody thought like, holy shit, this is happening, right? But as it turned out, a few hours later, it was all a coincidence. Really, nothing really else. And you might be thinking like, you know, no, it's not really that problematic. But the problem is, and this is one of the well-known examples, probably like, I think like 20 or 30 years old right now, but there was a radiation therapy machine that was used to be analog and used to be modified, you know, but eventually they made updated a version of this radiation therapy machine that was completely run by software. And there was a bug in that software, and that bug eventually killed 6 people. So you might be thinking it's fine, but I'm saying it really isn't. The problem is everything essentially right now runs on software. And sometimes the bug in the software, the thing that we produce as developers, as software engineers, might make some, you know, kid being unable to tie his shoes. But sometimes people will die, and I think this is a little bit problematic. We have this approach to writing software that it comes with no guarantees, and you know, as long as you don't deploy on Friday, you're good, right? Because I mean, it's software, right? That's the whole idea behind it. It's software. You can always change it. You can always deploy it. The biggest strength behind software, this flexibility, is also its biggest downfall. Some people like Uncle Bob will tell you like, oh, yes, there is a problem and you just need more discipline. The programmers are not really well disciplined. And I love this quote saying that Uncle Bob is saying that like the solution to people writing bad code is not to write bad code. And I think this is stupid. We are just humans, and people will make mistakes no matter how much they are disciplined. And we just need better techniques. Uncle Bob will tell you the only technique is to write more tests. And I do agree tests are one of the ways to guarantee correctness, but they are not the only technique that we have in our toolbox. The problem really is that the software became too complex. It it is sometimes described as developers trying to write a complex software are being compared to chess players who spend 80% of their time focusing and trying to realize where the pieces are on the board instead of focusing on the game itself. The problems are complex and are just too hard to comprehend by a single mind. Now, the thesis for this presentation is that there is this thing called formal methods that can actually help provide a better software. And what are formal methods? So roughly described, they are just a rigorous way of providing a specification and design, and especially verify that the computer system works. By verification, we mean ability to prove that whatever we wrote actually makes sense, actually works, and will not provide errors. Now, there was this a few years ago, a famous research which was funded by DARPA, where they tried to, the hypothesis was that formal methods can help with security bugs. And I really don't want to spend too much time on it, but I can only tell you that they have, like real roughly, they divided the research, like they had the two teams, red team and blue team. The blue team was just people who were well known in academia and well known in formal methods field, while the red team was, there was just a bunch of hackers. They in the phase 0, they proved there is a problem, so they took two machines. One was open source quadcopter, and one was actually Boeing's helicopter, which Boeing was really proud of. It was a helicopter that could be operated by a pilot, but could also be operated remotely. And what happened was without physical access, the red team could get access to both of those systems. They could fly the quadcopter easily. To surprise of Boeing engineers, they could also really easily fly the Boeing helicopter as well. So the thing that was already deployed in the U.S. Army, thing that was flying in mission-critical situations, could be easily taken control of, and that made people a little bit scared. On the phase 1, they just what they did was that they re-implemented the majority of functionalities of the quadcopters of the open source product, because basically that was easier. And they, using formal methods, within the 8 months period, they rewritten the whole kernel, the whole system for the quadcopter, with all the security properties were formally proven that they work correctly. So the things like memory safety, malform messages being ignored, and no unauthorized message being ignored as well. Red team had access to all the code base, to all the documentations. They could participate in all meetings from the blue team, and eventually, after 8 months period, they had like 6 weeks to crack the software, and they really couldn't. And I said I just want to briefly skip through it. But I'm just saying that on the phase 2. They did the exactly same thing with the Boeing helicopter, and they had an ability to actually deliver software for that helicopter to be unbreakable. So the red team was unable to crack the system, was unable to take control over the system whatsoever. Now, so the full story is available in this paper, but there's also a very good presentation from London conference Code Mesh, I think 2016 or 17, by one of the main researchers in that program. So I do encourage you guys to actually have a look. It's really interesting stuff. Now, the question might be, so why this, like, given the problems that we have, given the software complexity, given all that is really, 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 really hard piece of work that we have to do every day, and it kind of infects every portion of our life, why this is not becoming a standard? So there are two problems with it. Code verification and formal methods are hard. And if you look at the spectrum of the methods that you get when on the axis, you get, like, experience that you have to have being evaluated in the PhD years per lines of code, and on the y-axis you have like how much correctness and guarantees you get. The type system, so things like writing software with Haskell or Idris, is considered the least complex and giving the least safety. So it takes a lot of effort and a lot of knowledge to have ability to provide formal method security, and at the same time, it takes time to write proofs. So that is actually really, really hard. Second problem is that security, like, writing secure code for military, it's a well-known problem. We as software developers have to provide, we live in this agile environment, right? We have sprints, we have iterations. We not always know what we actually are delivering. Even our clients not fully aware of what they actually want. They are willing to pay us money, and they also would like us to actually realize what they really, really want. In that environment, it's really hard, I would say, to figure out and approach what formal methods and writing proofs would make sense. So to sum it up, software is very hard and impacts everything. Software is too complex to comprehend. Things will break eventually. There's nothing we can do about it. And formal methods are hard. Thank you very much, Q&A. Thank you. I guess I'm joking, right? You have to remember that there is hope. And that's why we have this talk, because this talk was supposed to be about TLA+. So you have to think about two different things. Code verifications, when you write proof for your software, versus system verification, when you try to prove that the overall design of your system makes sense. So instead of proving the code, which is hard and will consume time, there's a different trick that you can do. You can formally verify the overall system. So let me show you where the problem is. Imagine that you try to provide a banking system where Alice has ability to pay Bob, and somebody came up with an idea. Hey, this is how we're going to write this this software for this bank institution here. So there's going to be like those squares represents the variables that holds account for Alice and for Bob, and then there will be like variable for Bob where he can say like, I want to send $2. Step at this point checking whether the account that Bob has is he still able to pay $2 for Alice? Does he have enough money? And if that's okay, then that value is being subtracted from his account. It's being pushed on this message queue, and that travels over the network, and then eventually that money lands in the Alice account. Now, if you look at it, and you have, I guess, few months of experience as being a software developer, you already know the design is broken. You already know this thing will fail. You don't have to write any software. You don't have to write any line of code to realize that when things will run concurrently, things will break and we will have issues. So before you write any line of code, your design can already be broken. No matter how good the code eventually will be, your design at the beginning was broken. And you always are making design eventually. Sometimes you do a little bit of whiteboarding. Sometimes you maybe write a specification. Sometimes it might be you standing in the kitchen and having conversation. Hey, listen, I'm actually going to write this, microservice, and I'm going to send you a message X, and you have to do something about it. Yeah, okay, cool. See you, man, in an hour. And this is how you do your design. Regardless, the design is still happening. It would be good if we could verify that design is correct, because no matter how good the code will be, if design is broken, then the whole system will be broken. You might be thinking, but wait a minute, if design is broken and we write some code, eventually tests will show us that the things are not working correctly. So let me show you to a very well-known challenge that was happening like 20 years ago on an extreme programming forum. So the guy proposed, he said, this is a little bit of Java code, so I know it's just a Scala conference, apologies, but the guy proposed a very simple code that was just two methods being introduced, put and take, and he said, listen, there's a bug in this piece of software. Your challenge is to write tests that will show where the bug is. And people couldn't do it. People spent hours on it, and there were people popping out saying, this is bullcrap, this challenge doesn't make any much sense because there essentially is no bug in this software. And so the guy the guy who proposed the challenge, he eventually showed the sequence of steps of computation to where there will be a problem, but the problem was essentially a deadlock. If you have multiple threads running, executing those two methods, eventually there would be a deadlock and the system would be broken. Now, when he showed the sequence of computation, he said, listen, now that you guys know what the problem is, Still, the challenge is to write the test that will guarantee, like, will show the problem exists. It took 16 hours of pure work, and the guy who did it, who delivered it, counted how much time it took him. It took 16 hours to actually write a test, and that test needed to, I think, run on 11 threads. They had to be executed at least 250 times in order to break from time to time. So the overall here, the idea behind this slide is that, unfortunately, when concurrency and parallel computation kicks in, the integration tests will not save you. And they sometimes might give you positive feedback, false positives. When there is a bug, they will turn green, and then you will go with that to production. So how can we verify the design? We can verify the design with TLA+. So TLA+ was created by Leslie Lampert. If you don't know who that person is, you really should right now open Wikipedia. But I will leave you maybe for lunch to read about Leslie Lampert. Just skip, because we have probably like 20 minutes, not more. The overall idea behind TLA+ is that you can represent any concurrent program as a sequence of steps in a sequential program. So you can simulate concurrent program as a sequential program. So, and you can represent that as a sort of like state machine. So you can represent that as your program going from one state of execution to another. So there is a concept of a state. There is also concept of an action. So action represents this ability to go from one step to another. If you have, so you can imagine you have one state from which two potential things can happen because they run in parallel, then you will have two separate actions that can, in general, go to two different states. And there is also a concept of behavior. So behavior is a sequence of actions, potentially infinite. And here on the right-hand side, you guys can see a very simple program represented in this way with states, actions, and behaviors. But in general, it doesn't look really that simple. It looks a little bit more like this. So TLA+ is a language that allows us to specify our system in terms of states and actions. But that's only a specification. So you might be thinking, okay, so where the verification part kicks in? And the verification part comes with a program that TLA+ comes with, which is called TLC. And funny thing about TLC is that nobody really right now know what the TLC stands for. You will find papers in Google, you will find papers like stating TLC, talking about TLC, but everybody forgot what that really means. So, but TLC is nothing else as a model checker. What it will do, it will take your specification. So when you design, you specify your software as a terms of states and actions that can go from one state to another, it will just run a brute force on your specification, and it will go through all possible states, through all possible actions, and it will try to verify whether some capabilities of your system that you would like to have in your system are in place, if some liveness properties are in place as well. So the safety properties and liveness properties, the safety really means that it's checking whether your system is in all possible states, whether this can break. And what do we mean by break? We might say that, for example, if you're writing a software that for example, you're writing an algorithm that's supposed to elect a leader, and you would like to in the processes, and you only like to have a situation where there are either no leaders elected, or there's always one leader elected. You don't want to have a scenario where by any chance two leaders were elected. You can have that invariant, you can have that property being defined, and then TLC goes through your design, goes through all the states that are possible in your system and checks if that particular property was violated, yes or no. Now, it is possible that you write an algorithm that will never violate that property, right? You might be writing algorithm to elect a leader in some group of processes, but they will just always not elect a leader, and that safety property will hold. while your design is still broken. So the next thing that we also check is liveness. So liveness checks whether the system eventually progress, and that's what you always would like to check when you write specifications. Now, the language of TLA class basically use math, nothing else. So you have things from logic like and, or, negation, and implication. You have like there exists, or for all. Hopefully, you guys are familiar with it. There are elements in the language from set view, like empty set, element exists, or union or intersection of sets. And there also are a few elements from something which is called temporal logic. And by the way, this is not an accident. This is not the Unicode that didn't load up. Those are actually valid symbols from temporal logic. So the square is telling you that something always should happen. So temporal logic is logic with time. So you want to say this property always holds, while the diamond, so the other operator, is saying I want this property I want this thing to eventually happen. So you can write properties like, given this thing will happen, eventually that thing will happen. And this is how we represent it. Obviously, they have like ASCII representation. But yeah, let's move on. So let's actually try to write some TLA class with it. So as I said, we have states and we have actions. And the way you write TLA class, you define two things really. You define initial formula. So that formula generates the initial state. You're stating what is the initial state in my system. And then also you have to provide the next step formula. So this formula is saying, given that we are in this particular state, and there is a next state over here. Actually, can I stop sharing? You guys see me? Hopefully you guys see me. All right. So the idea behind the next formula is that I'm in this state over here, and there is a state over here. I want to know if I can go from this state to that state, if that's valid. So that next formula returns a Boolean value, true or false, whether this is possible to go from one state to the other or not. Do you guys see the screen one more time? Hopefully. Yep. Thumbs up. Yep. All right. So I said TLA class is not used to specify code, but I will use code at the very beginning. I have hopefully 15 minutes. I will just use code to show you guys the simplest TLA class that we can write. So imagine that you have this little piece of code. You have some variable x, which is equals to 5. You have a list of integers. Let's say there are 3 elements in that list. And what we will do is we will assign to x some element from that list, some random element from that list. And if we will try to right now think how many states the system has, the system is not really complicated, right? It starts with the variable equals to 5, the variable x equals to 5, and eventually it can be equal the first element from the list, the second, or the third. How the TLA class representing this piece of software would look like. So we import some modules here, integers. We say constants candidate. So this represents that list of 3 integers. This represents a constant and something that will not change in our system. And then we declare a list of variables. So here the variable x that we seen in that code a moment ago. So now we're saying, as you remember, we have to provide 2 formulas. The initial formula that provides us initial state, and also the next state formula, so that the formula that takes 2 states and says whether this is possible to go from one state to the other. So the initial formula, we initialize our variable x to 0, and we also provide a variable that exists implicitly, a program counter, stating what's the current state of our program, which we call, for example, here running. So this is the state of our system when the program starts. And then we say, when is it possible to go to a given state? So we're saying, if we are in the state running, and I'm sorry, and if you're going to see right now the x with a hyphen, whenever you see a variable name with a hyphen, that means that we are referencing the value of that variable in the next state. So when you see PC, it means that PC in the current state that we are in. When you see PC with a hyphen, it would mean that you are referencing the variable PC in the next state. So here we are saying that the value of X in the next state has to be anything in something in the set that is being defined in the set of candidates. And then we also say that it is possible to go to the next state only if the PC counter is changing from running to stopped. Now, when we define our little simple program like that with a TLA plus, the number of states look essentially like this. And you might be thinking, all right, like there's a lot of complexity. Like you showed us a very simple Scala code, and there's like tremendous amount of weirdness in the TLA plus. What the hell? Where is the value? As I said, it's really hard to do a presentation about the TLA plus because you either want to show a code or you want to show the motivation why you would like to use TLA plus in the first place. I try to do both. Hopefully, I will not fail, but it is a recipe for disaster. Now, all right, so let's I will right now show you. We have like 10 minutes, and I will right now show you. We'll slowly go into a little bit more complex stuff with TLA plus, but I will not be digging into the very details of the language itself. Let's make one thing clear. The idea behind this presentation is that, and actually, all right. So the idea behind this presentation is following. You have to remember, you see the language, the syntax of the language for the first time. It will look bizarre. It will look weird. It's obvious because you haven't seen it before. It's a little bit different when what you used to see when you do Scala or Java or whatever. Now, remember, this is only syntax. Syntax is always weird when you see it for the first time. Try to show a little bit of your beautiful Scala code to your grandma, and she'll be like, what? And the same thing goes with any other language that you've never used. What I will try to show you is that, essentially, TLA plus is not magic. The formal methods are not complicated if you use a formal verification of the design with such tools as TLA plus. And you have to just try to think over the specification. Imagine that eventually, after a week of playing with TLA plus, you're accustom yourself with the syntax itself. Try to see what that actually will give you eventually. So, all right. So let me get back to my screen sharing. Start screen sharing. I don't know if you guys remember this game, but the idea behind this game that you have to put the circles from one stick to the other. The rules are simple. You can only place one circle at a time, and you can put the circle on an empty spot, or you can put that circle on some other circle as long the circle that already is placed has to be bigger than the one that you're putting. And we would like to write a little bit of TLA plus to check if that is kind of solve this puzzle. So what you're going to see right now is a little bit of that code. So we have we are defining three variables: tower 1, tower 2, and tower 3. We are also extending our specification with a module called sequence. And now initial state formula says that we have those three variables, and the first tower has those circles where each number represents a circle, 1 being smaller than 2, obviously, and tower 2 and tower 3 are empty. And we want to say what it means, what is a valid step from going to one state of this puzzle to the next one. So we are saying you can either pop an element from tower 2, or pop element from tower 1, or pop element from tower 3. What does it mean to pop element from tower 1? When it means either you pop an element from tower 1 and place it on tower 2, or pop an element from tower 1 and place it on tower 3. Fine. What does it mean to take an element from tower 1 and place it on tower 2? Well, first of all, tower 1 cannot be empty, right? So the symbol here, the hash, means it's not empty. Secondly, tower 2 can be either empty or tower 2 is not empty, and the first element on tower 1 is smaller than the first element of tower 2. If those are valid, then we are saying after this change on the next state, the tower 1 that will look as a tail of tower 1, and tower 2 will be concatenation of tower 2 and the first element from tower 1. And we also are stating that tower 3 will not change. Will be just left as it was. Now, what you're seeing here is, I don't know, thumbs up or thumbs down, how big is this font? Do you guys see it? I can probably zoom it a little bit. Thumbs down, yeah, okay. So the code that you seen just a moment ago is pretty much here. What we will do is we can now, and I will zoom the important places, don't worry about it. We create a new model, we give it a name. In that model, and let me right now try to zoom it. Yeah, in that model, we are saying, what is our initial formula? So this is what we defined. What is our next step? And then having that, we can actually run the software. So now TLA checker is running. It's like this brute force is going through the software. And that gives you, and then eventually we learn that in that system, we had 81 distinct states. And given those, we have those states, well, now the question would be, how do we solve that puzzle? Well, remember how I mentioned the TLA checker will check for those properties for invariants. We can provide an invariant saying that never in this puzzle will we have a situation where tower 1 and tower 2 are empty and tower 3 is 1, 2, 3, 4. And if we put that in variant, so you probably don't see it. Sorry. So like I'm saying, this represents not, and we are saying what we don't like to see. And now, if we run it, the TLC checker will give us a counterexample. So here, let me try to zoom it one more time. So here we're saying this is the initial state that we start with, and then what? We pop out the first element and put it on tower 2, and the second one and put it on tower 3, and then it goes like that. And eventually after 16 steps, we end up in that puzzle being solved. But I do understand this is like a little puzzle, and this is not really anything about writing software. And I also understand that you guys have lunch, and I have 5 minutes. So, you guys remember this example that we've seen before, the Alice and Bob, and I said the design is broken. There's no point of writing code whatsoever if the design is broken. Well, let's try to actually design the software using TLA+. So we will say there's some initial value that the Alice and Bob have. There are clients that will operate as for Alice and Bob, a computer, a mobile phone, and whatever. And there's a maximum amount of money that you can wire when sending money between Alice and Bob. And those variables, like a variable representing Alice, Alice messages, and what Alice picks as a next value to send over the wire. And we initialize those values. What's important is the next step. And don't worry, I know you guys have lunch, so we will not go into details, but stay with me. This is the nice part. You can actually see that the names here will represent the vocabulary that you use when you talk with your clients, you use when you talk with the business side in your company. So you might be saying, okay, so there are a number of possibilities that can happen in the system. Either Alice retrieves the money or Bob retrieves money, or there exists a client. So this /e means exists a client of a little set of clients such that either Alice will prepare some amount of money to wire using this client, or Alice will wire some amount of money using this client. And the same thing applies to Bob. Now, there are two invariants that we would like to see in our system. So we would like to check that no matter what happened, no matter what different configurations will happen, eventually there will be not a situation in which Alice has less money than 0. 0 and every positive number is okay. Anything negative, it means the design is broken. Now, if we run the system, we can specify it. We can put those invariants here in this section about invariants. We've also defined our constants. So we said like initial value for Bob and Alice is 10, max wire is 3, and we have 2 clients, and clients can be just represented as strings. That doesn't really matter. We run this model checker, and everything is fine. No errors, right? Because we still have only 2 clients, but each client representing a single user in the system. However, what happens if we modify the Bob client set? Instead of saying there is one client, we will say there are 2. Given that we do that, and we run the system, and if we run it, the model checker will quickly give us a counterexample. In that counterexample over here, it's saying it had prepared for Bob 2 wires, and those were valid. So the amount of money that the Bob had was 2, and he prepared to 2 different clients prepared to wire money, and the validation went through. So one client succeeded, so he sent this money, and this made the Bob amount equal to 0, and the other one tried to do it as well, which ended up with Bob having -$2 in the system, which broke the invariant, and the TLC plus will give you a counterexample. You guys, I know I have 1 minute, so you guys, I'm aware of it. So you guys know probably event sourcing and CQRS. Hands up. You guys aware of what CQRS? Yeah, everybody. Also, I don't have to explain this. Great. Now check this out. You can define CQRS design behind event sourcing and CQRS with those little steps. Like you have an empty, you have a list of commands, you have your event store, you have a view that represents eventually consistent view, and then you can say that the client can generate command, or the command is validated, or the system updates you. All that you can represent in the system. So while somebody is drawing a design on the whiteboard, and you have this little design meeting, you can, if you're efficient in TLA plus, you can at the same time type this design in the specification itself, and then you can provide this little invariant saying that always whatever is in the event store will be represented in the view. And we know that's not actually the case. We know that this design is eventually consistent. We know that there will be scenarios where this will break, right? So what you can do is you can provide a little bit more complex formulas, temporal formulas. So that's what TLA stands for. TLA stands for temporal logic of actions. And here we are saying, so this invariant is telling us that for every event that is possible to be generated, you don't care which one, for every possible event that can ever be generated in the system, if that event ends up in the event store, so if eventually it's persisted in the event store, this little thinking, you read it as leads to, then it leads to that eventually that system you want to see in the view. So now here you just represented the eventual consistency in the CQRS and event store kind of paradigm, and you can run it, you can check it with the TLC plus, and it will show you that is actually the case. And I don't have time going through examples how those are being used in production. I will post those slides online so you guys can have a look. But TLA plus help a lot through Amazon microsystems and all that. But important thing is that for the thing you guys to remember, if you spend a little bit of time with TL plus, give it a go, give it a weekend. There's an amazing video course given by Leslie Lampert. It's like 10 different videos, each 15 to 20 minutes long, so you can watch it while eating your lunch. It gives you all the knowledge that you need to actually start writing software with TLA plus. And I'm just saying, give it a try. It will be hard at the beginning because it's something different. The syntax is different, but the amount of stuff that you can actually prove, and you don't need to do rocket science. You don't need to implement airplane software or security software. Give it a go with whatever you do, and I guarantee this will give you an effects that you are not aware of, and you will find bugs before you write a single line of code. Especially that because that gives you a little bit of God lenses, it can gives you ability to check things which you normally would not be able to check with tests. Now, important thing is that TLA plus will not generate source code for you. This is not UML all over again. We are not going back to the 90s. We will be not generating code from specification. The idea behind it is just to check whether the design, something that you just created in your head makes sense before you start implementing it. There's still a lot of work and correctness and discipline, I guess, going from that specification to the actual code. But that's not where the TL plus will help you. Some links. I probably extended my time. So my name is Paweł Szulc. So this is Twitter for you to complain. I can run the QA session on Slack if you guys want. I know you guys want to run for lunch right now, so I'll not hold you for questions. But I am available on Slack. So if you have any questions, let me know. I can answer those questions on Twitter. My messages are open, so just guys let me know. Thank you for staying with me. I know it's a weird running remote session, but I hope I was able to a little bit provide. And lastly, and this is important, don't after this talk give TLA plus a chance. Basically, just during the weekend, play Leslie Lamport videos, give it a go, and I guarantee you will be satisfied. And it's not really that complicated as it seems. And you can always brag in the company that you are the only person here who knows the formal methods, and then maybe get a pay raise. All right, guys, thank you very much for your time, and see you hopefully next year. See you guys.